What can travel through any substance without you ever knowing it's there? Ghosts, yes, but also ghost particles, or neutrinos as they're officially named. Neutrinos are providing new ways to approach some of the biggest questions in particle physics, and Kirsty Duffy is at the epicentre of this research at the University of Oxford. Kirsty joined me to elaborate on the potential of neutrinos, where they've come from, and where they could take science in the future.
Kirsty, thank you so much for joining me to record an episode just before you give your talk in the theatre downstairs, literally below our feet.
Yeah, thank you very much for having me.
You are a particle physicist specialising in neutrinos. Neutrinos have quite an ominous nickname of the ghost particle, which I think has probably helped their PR and get them a fair amount of attention in popular culture and films specifically. People might remember that neutrinos were actually the root cause of all the natural disasters that kicked off in 2012, the disaster film. So they were first on the call sheet for that one. But where does the nickname of the ghost particle come from? And what does it actually mean to be a ghost particle?
It's funny that you bring up the movie 2012 because the specific problem in that film, I think, is the neutrinos from the sun are mutating. Mm-hmm. And I think we will talk later. The neutrinos from the sun do mutate. And that's one of the reasons they're so interesting.
Yeah.
So I, as a little baby physicist, found that very fun. But neutrinos are called the ghost particle because they go through everything just like ghosts. They almost never interact. If you look at your thumbnail, about 100 billion, with a B, neutrinos pass through your thumbnail every second. And they're not just magically focused on your thumbnail, they're streaming through your entire body all the time. In your entire lifetime, on average, 1 or 2 neutrinos will likely actually hit an atom in your body, and the rest of them just go straight through us. So they're called the ghost particle because they act very much like ghosts. And I mean, most physicists, the thing they know about neutrinos is that you can't measure them. So if you're a physicist who works at CERN, the synonym for neutrinos is missing energy. And they literally infer the fact that a neutrino is there by the fact that they haven't measured something. So trying to actually study them can be quite tricky. And it means we have to have really, really huge neutrino detectors, often under mountains or in mines. But it also makes it a lot of fun. And it's one of the reasons that I think neutrinos are slightly less well understood than other particles because, you know, they haven't been as well studied in the past. And for me, that's what makes it exciting.
So to put neutrinos into the wider context of some of those particles that people maybe are a little bit more familiar with, how do the properties of neutrinos compare to particles like protons and neutrons and those which people have maybe heard of or come across in science before?
So neutrinos are the most abundant matter particle in the universe. For every 1 proton, neutron, or electron in the universe, there are about 1 billion neutrinos.
Oh, okay.
Yeah, they're really everywhere. But because they're ghosts, you don't notice.
Sure.
They are much, much lighter than all the other particles. That is a mystery about neutrinos that we don't really understand. Originally, in fact, they were thought to have no mass at all. We now know that they do have a mass, but it is so light we've never been able to measure it. Neutrinos interact much less than any of the other particles. So a neutrino is about 1 million times less likely to interact with something than an electron. And in particle physics, we often talk about the probability that something interacts with an analogy of the size. We define something called the cross-section. And if you think about in sort of normal physics, a cross-sectional area of something is the size that it takes up. So, for example, if I throw a ball at you, the cross-section of that ball is the size of the 2D circle that you see when it's flying towards you. If you are inside that circle, you're going to get hit by the ball. And if you're outside it, you won't. And so if the ball is bigger, it has a larger cross-section, it's more likely to hit you. By that sort of an analogy, if an electron was the size of a beach ball, a neutrino would be the size of a grain of sand. So they're much, much less likely to interact with anything and much, much lighter and much smaller, but also a lot more common than the other particles.
So you said that it's roughly twice in your lifetime that a neutrino will interact with an atom in your body. What happens if that does happen, or is it just an average and sometimes it happens but there's no kind of marker for you to be able to tell?
It's just an average. Sometimes it happens, sometimes it doesn't. There are a few different things that can happen if a neutrino interacts with an atom in your body. If it's an electron neutrino, we'll get into this, but there are three types of neutrino. One of those is electron neutrino. If it's one of those, it can do something called inverse beta decay. So beta decay is where a neutron turns into a proton, an electron, and an electron antineutrino. Inverse beta decay is where an electron neutrino triggers a proton to turn into a neutron and an anti-electron. So that could change an atom in your body from one element to the one next to it on the periodic table. I don't think that would do much. Out of all the atoms in your body, I don't think you would notice. But it would be a very, very tiny change.
So let's unpack those types of neutrinos. What are they?
There are three types. They're called electron, muon, and tau neutrinos. Maybe one thing to say first is in particle physics, we talk about three generations of matter. So everything you've ever touched, felt, heard, seen is first generation. That's our electrons, and it's the up and down quarks that make up protons and neutrons. But we have discovered that there seem to be a sort of matching set of particles that behave very similarly to those ones, but are all heavier. We call those the second generation. And then there's a third set that, again, seem very similar, but they're heavier again. And so the muon is the second generation version of the electron. It's about 200 times heavier than the electron. But other than that, it behaves exactly the same. It has all the same types of interactions. And then the tau lepton is about 200 times heavier than the muon. And each of those has a sort of paired neutrino. And they're really paired together in that if an electron neutrino interacts with something, it will produce an electron. If a muon neutrino interacts with something, it will produce a muon. And if a tau neutrino interacts with something, it will produce a tau.
This is obviously a very complex area of research that seems to have exciting new developments basically every other month. Whenever I'm researching episodes, I'll search the kind of broad field and just go on news on Google. And for neutrinos, it's popping off in that area. But when were they first discovered, and what did that process look like?
Yeah, so neutrinos were first proposed in 1930 by Wolfgang Pauli. At the time, there was a big crisis in physics going on because they had measured electrons produced in beta decay. At the time, they believed that beta decay is a process that turns a neutron into a proton and an electron. And that's a two-body decay. If the neutron is at rest and the proton is at rest, you can calculate exactly what the energy of the outgoing electron will be. And so they expected that when they measured these electrons, they would see the same energy every time. And what they saw when they did that was, in fact, a spread of energies across quite a range. And that caused a real crisis in physics. People were ready to throw out the idea of conservation of energy and really sort of go back to the drawing board and start again. And in 1930, there's a really famous letter from Wolfgang Pauli to members of a radioactivity conference in Tübingen, saying that he is unable to deliver this news himself because he is indispensable at a ball in Zurich, but he's come up with an idea to save the principle of conservation of energy.
Great.
And that is that there's a third particle being produced that he called the neutron, close enough. And he said it has to be electrically neutral, have no mass, and be completely undetectable. And the reason that we're seeing this range of energies in the electrons is that some unknown amount of energy in each interaction is being carried away by the neutrino, and that's impossible to measure because these are new particles that you can't measure. So that was great because it saved, physics as we knew it. But Pauli was really upset by this idea that he had invented something that was impossible to detect. He had a quote where he said, "I have done a terrible thing. I have postulated a particle that cannot be detected." However, he was not quite right because it is possible to detect neutrinos. It's very rare, as we've already talked about, but it is possible. So there were two scientists who I think started looking into this probably fairly soon. I'm actually not sure when. They were called Fred Reinus and Clyde Cowan, and they set out to try and measure neutrinos. They knew neutrinos were produced in nuclear reactions. They were scientists at Los Alamos in the 1940s, and so their first instinct was to use a test nuclear bomb.
Sure.
And this actually, it was approved. You might think that setting off a bomb very close to your particle detector is not the best way to have a particle detector at the end, but they thought about that. They were going to set off the bomb and at the same time drop the detector down a shaft so that while the Earth was shaking because of the bomb, the detector would be in free fall and would be protected. And then it would land on something soft. I'm sure they'd worked out the details at the bottom, and they would measure their neutrinos. Probably fortunately for everyone, but maybe unfortunately for fans of chaos, before they actually got to doing it, someone said, if they're created in nuclear interactions, why don't you just run it next to a nuclear reactor?
Boring, but fair.
Yeah. So they took their detector off, they put it next to a nuclear reactor, and it took until about 1956 before they actually had sort of incontrovertible proof that they had discovered the electron neutrino. And they wrote to Pauli, who was, I think, presenting a seminar at CERN at the time. And apparently he and his friends drank an entire case of champagne to celebrate that night.
As they should.
Exactly.
I mean, they did what he thought would have been impossible.
Yeah,
so if that's not the time to drink a case, I don't know when it is.
Yeah.
And what for you have been some of the most surprising or interesting realizations since then to now in neutrino science?
So I sort of hinted about this at the beginning. Neutrinos have continued to surprise us. Originally, people thought there was only one neutrino. Subsequent experiments found a neutrino that only seemed to produce muons, and then another one that only seemed to produce tau leptons. So we now think there are 3 types. But the real change happened sort of in around the 1960s. There was a chemist actually called Ray Davies at Brookhaven National Lab. And I think in those days, if you worked for a national lab in the US, they just said to you, do some science. And so he took the job, he did some reading, he found out about these things called neutrinos, thought they sounded like fun. He knew, well, everyone knew at the time that a lot of neutrinos are produced in the sun. And so he set out to build an experiment that would detect neutrinos from the sun and use that to test the models of how the sun works and the fusion processes that are going on in there. He built an experiment that was 600 tons of cleaning fluid.
Okay.
Yeah. There's pictures of him swimming, not in the cleaning fluid. I don't think it's water.
Yeah, okay.
But still, it was a big experiment. It was in a mine in South Dakota, an old gold mine. The idea was that if an electron neutrino from the sun interacted with an atom of chlorine in the cleaning fluid, it would turn it into an atom of argon. And they would then count the number of argon atoms and use that to work out how many neutrinos had interacted. Out of these 600 tons of cleaning fluid that he was running, he expected about 36 atoms of argon per month. So it was an incredibly precise experiment to do and very, very difficult. They ran for a really long time because it's also a low statistics experiment. So they ran for decades, I think, and finally came up with an answer that was about 40% of the predicted number of neutrinos based on the models of what was happening in the sun. And at the time, people said, well, it was a difficult experiment.
Yeah.
You were measuring tens of atoms out of hundreds of tons. Well done you got within a factor of 2.
Well, yeah.
But it turns out the experiment wasn't wrong. It has since been confirmed by other experiments. What Ray Davies thought at the time was that the models of the sun were wrong, which is also fair. It's not like we can go up and see what's going on.
Yeah.
But it turns out that was not the answer either. In 2001, there was an experiment called SNO, the Sudbury Neutrino Observatory, which ran in Canada. And they repeated the experiment that Davies had done, I think with different atoms, but they had a way of measuring neutrinos that was only sensitive to electron neutrinos, and they confirmed that they also got about 40% of the number they expected. But they had a second way of measuring neutrinos that was sensitive to all 3 types, and that got the right number. And so what we think is happening now is that even though only electron neutrinos are produced in the sun, as they travel between the sun and Earth, they are changing into the other 2 types, which is really cool. So these particles that we thought were completely different particles, it turns out are actually not, and they can sort of flip between the different types as they travel. The other thing for me as a person that works in this field is that, this isn't a discovery that only happened in 2001. So it feels like it's still a very recent field with a lot of really exciting stuff happening now.
Does that mean that what happened in the film 2012 isn't that far off something that is scientifically plausible?
I mean, yes and no. So yes, the neutrinos from the sun are mutating. But I think in 2012, somehow that makes the ocean boil.
Yeah, I think it just seems to make everything bad that could happen.
Yeah.
And maybe that's the thing that's a bit of a stretch.
Yeah, I mean, the thing that you can't get over is that neutrinos still basically do nothing. So even if it's a different type of neutrino, you can't make it interact more.
So that big realization, 2001, in terms of science, a lot of areas of science, that's pretty recent.
Mm-hmm.
But it's also still 25 years ago. So what has happened since then? What do we know now that's built on that learning?
We've got a much better understanding of how the neutrinos are changing. So around the same time, actually, slightly earlier, possibly even late 90s, there was another experiment called Super Kamiokande that measured muon neutrinos that are produced in the upper atmosphere. And what they showed is that the muon neutrinos also seem to disappear, but it depends on how far they've traveled. So the ones that have come all the way from the other side of the Earth are disappearing at a higher rate than the ones that have come a relatively short distance from the atmosphere just above us. And that has confirmed a theory called neutrino oscillation, which is the flavor of neutrinos changes as a function of how far it travels. And in fact, it oscillates back and forth. So if you go far enough, it'll come back round again and you'll get your muon neutrinos back again. These days, there are a few different ways we study them. My research is focused on what we call long baseline accelerator neutrino oscillation experiments. So this is where we create neutrinos with particle accelerators. That means we know what we're making. There's no maybe you don't know what's going on in the sun problems.
Yep.
Just to be sure, we measure them just after we've created them in what we call a near detector, because we're really inventive at naming things.
Well, you know what it does.
Yeah,
least.
exactly. It's near and it detects neutrinos. And then we let them travel some long distance, usually sort of hundreds or thousands of kilometers. And then we measure them again. And we're looking to see the original neutrino flavor disappearing and other flavors of neutrinos appearing. Doing that, and with other experiments that are measuring, again, neutrinos from the sun and neutrinos from the atmosphere, we have been able to really pin down how exactly the neutrinos are changing. We have a good sense now of the underlying parameters in the theory that can determine how the neutrinos change. But there are a couple we're still working on. So again, relatively recently in physics terms, but still probably 10, 15 years ago, we measured the last parameter that means it is possible for neutrino oscillation to be different for neutrinos and antineutrinos. So that is quite exciting, and that opens up a lot of potential questions that we can go into. There's also been real developments in other areas. People have detected neutrinos from way out in the galaxy with way higher energies than we ever expected to see. People have detected really low energy neutrinos from the sun and even coming up from the center of the Earth. And people have started doing measurements to try and even understand what the masses of the neutrinos are. So there's a lot of things we've learned, but there's possibly even more things that we now know we don't know.
One of the big questions or areas that neutrinos could hold some sort of key to answering in vague terms is to do with the Big Bang and antimatter. So to get a kind of baseline before we go into the nuances of the antiparticles and how they compare to their respective particles, when we're talking about matter and antimatter, how do we differentiate between the two?
I like to say that matter and antimatter are the same but opposite.
Okay.
And what I mean by that is every particle that we know about in what we call the standard model of particle physics has a matching antimatter particle that would be the same mass, but everything else about it would be different. So it would have the opposite charge. It would have the opposite parity, which is a very mathematical term in particle physics, but it's basically related to looking in a mirror and how if you reflect the world in the mirror, everything is opposite. If I lift up my right hand, the mirror, Kirsty, lifts up her left hand.
Yeah.
And so changing those two things, charge and parity, is what differentiates matter and antimatter.
So what instances do we see antimatter in the universe?
We see antimatter not particularly often in the universe. We can create it in particle accelerators. We do see it created, for example, a beta decay will produce a neutron will turn into a proton, an electron, and an electron antineutrino, and that is a particle of antimatter. But big picture, the universe seems to be made of matter. And I think that's where you're going with the Big Bang question.
Yes. So what does this have to do with the Big Bang? And how does matter and antimatter change as a result of that? Or where does that come into the conversation?
So particle physics is really about symmetries. And it likes everything to be really nice and symmetric. One of the things that it likes to be symmetric is the total number of particles. And if you count a particle as plus one particle, you would count an antiparticle as minus one. So you might have heard the sort of Einstein E equals mc squared tells you that you can convert energy into mass. The subtlety that doesn't tell you is that you can't change the total number of particles. So if you have energy that changes into mass, it has to produce a particle and an antiparticle so that when we're adding up all the numbers, they can cancel each other out. All of our theories say that in the Big Bang, there was something that converted a lot of energy into a lot of mass, but that should have produced the same amount of particles and antiparticles.
Yeah.
The other thing we know is that if a particle and an antiparticle come together, they annihilate. They destroy each other, there's a burst of energy, and there's nothing left over. And so one of the big questions in physics is why that hasn't happened to our universe. You would think in the nearly 14 billion years since the Big Bang that even just randomly, those particles of matter and antimatter would have bumped into each other and would have annihilated.
Sure.
And even stranger, somehow it seems like only the antimatter has disappeared.
So enter neutrinos. What do they tell us in that?
The answer to this problem has to be that somehow physics is different for particles and antiparticles in a way that caused the antimatter to disappear faster than the matter did. Because particle physics loves symmetry so much, there isn't really much room for differences. We have seen some difference at CERN in some of the particles they've measured there, but the differences they've seen haven't been big enough to explain the total imbalance between matter and antimatter that we seem to have. Neutrinos are interesting because they are the place we haven't looked yet. They're the only particles I think that we know about that we haven't really been able to study to see if they're different yet. The link between neutrinos that we see around us today and being different between matter and antimatter and the Big Bang, I will be honest, is a little bit tenuous.
Sure, okay.
And it requires a few things to be true that we don't know. So if we measure differences in the neutrinos that we see, we don't think that directly would have created an imbalance in the early universe. However, there are theories that, I'm just going to casually drop this in there, there's theories that neutrinos could be their own antiparticles.
Okay.
Which is not super related, other than those theories rely on there being some heavy neutrinos that would decay. And so the idea is that in the early universe, there would have been these heavy neutrinos. We don't see them anymore because they've all decayed away. But the way that they decayed, if that was different for the heavy neutrinos and the heavy antineutrinos, that could have produced this imbalance between matter and antimatter in the early universe that would then have trickled through to the universe that we have today. It relies on a number of things being true that we have absolutely no idea if they're true. On the other hand, if this isn't it, then we need something else. And we don't know what that would be either.
You're currently based at the University of Oxford, but you have spent a lot of time at Fermilab in Illinois, in the US. And we'll get into everything you have done and still do at Fermilab. But to start with, you host a really great series on YouTube, on their YouTube channel, which really helped me researching this podcast, which is about all things neutrinos, and it's called Even Bananas.
Yeah.
Why is it called Even Bananas?
It's called Even Bananas. So, okay, in our original brainstorming meetings, the idea was everything produces neutrinos, even bananas.
Okay, sure.
Because bananas are high in potassium. Potassium is radioactive, and specifically it beta decays. So bananas are a source of antineutrinos. They're a relatively small source of neutrinos. No one is getting irradiated by their fruit bowl.
Sure.
But they're there. When we first released the first episode, we had a logo that had 3 bananas because there are 3 different types of neutrinos.
Mm-hmm.
And the number one comment on that YouTube video is, why is it called even bananas when there's 3 bananas in the logo?
Oh, because of even and odd.
Yeah.
Right.
None of us, it didn't even occur to us.
Oh, but because you know the intention behind it.
Right.
It's hard to see those.
I wasn't even seeing that meaning of even.
Yeah.
Yeah. Anyway, we changed the intro.
Mm-hmm.
So now it flashes through a few different things that make neutrinos and ends with banana.
So now that we've established that was just partly for my own interest, Fermilab has been home to hugely important experiments into neutrinos, many of which you've worked on during your time there. And you're currently working on the June experiment. Could you explain a little bit what this experiment is looking at?
June is a future experiment that doesn't quite exist yet, that will do this measurement of neutrinos using a particle accelerator. So there are sort of 2 centers in the world where we have particle accelerators that make neutrinos, Fermilab in the US and JParc in Japan. Both of them have currently been running experiments that do what I said. You make the neutrinos, you detect them with a near detector, fire them some long distance, and then you detect them again. And fun fact, when we fire them some long distance, we don't need to dig a tunnel for them because the neutrinos never interact. So you just sort of take your particle accelerator, you point it slightly downwards into the ground because of the curvature of the Earth. Mm-hmm. And then you let the neutrinos fly, the Earth sort of curves over the top. And if you've got the angle right, they pop out again at the point you want them to.
That is awesome.
Isn't it cool?
That's so great.
So the experiments that we're running at the moment are called T2K and NOVA. They have made really good measurements of neutrino oscillation, but it's become clear that they're not going to be able to measure certain things about neutrinos, and especially to say definitively whether there's a difference in how neutrinos and antineutrinos oscillate. So the next generation of experiments is going to be Hyperkamiokande in Japan and June in the US. June stands for the Deep Underground Neutrino Experiment. So we will use the world's most intense neutrino beam that will be built at Fermilab. We'll measure the neutrinos on site at Fermilab, and then we will send them, I think it's 1,300 kilometers to South Dakota, actually to the same mine where Ray Davis did his original neutrino experiment. Yeah, which is really cool.
That was intentional.
I think a lot of
coincidence.
physicists find it really cool.
Yeah.
I think it's probably also that it is lab space owned by the US government and therefore
sure.
is available.
Makes sense.
But for us, it makes it really
connection.
special. Yeah. We've excavated new caverns a mile underground, 1.5 kilometers below ground, to hold absolutely huge neutrino detectors. Because, I mean, as we've said, one of the limiting factors in how well we can measure neutrinos is just getting them to interact so you can measure them. And particularly when you're over 1,000 kilometers away from where the neutrinos are being produced, the neutrino beam sort of spreads out like a torch. And so the number of neutrinos that are actually passing through your detector is relatively small. And so we can maximize the number that we can measure by making our detector really big. Mm-hmm. So the idea is we're going to eventually have 4 detectors. Each of them is going to be 66 meters long, which these are numbers that make no sense and they sort of mean nothing. But if we were to fly from here to Fermilab, we'd most likely be on a 787 Dreamliner plane. And those are only 57 meters long. So
wow,
these are huge detectors. Each of them is going to contain 17,000 tons of liquid argon, which we'll use to measure the neutrinos. Fun fact, since we're here, argon was first isolated at the Royal Institution.
It was
in 1894.
I think what floor are we on? 5, 6 floors below us?
That's very cool. So the aim of June is we're going to be able to measure neutrinos with a sort of precision that we've never been able to do before. The way these argon detectors work, we will read them out using planes of wires that are spaced 5 millimeters apart. And so essentially we're going to get 5 millimeter pixel resolution over a 66 meter distance. So we're going to get sort of incredible precision measurements of neutrinos. more neutrinos than we've ever generated before from the particle accelerator, and we're going to be able to make the definitive measurements of neutrino oscillation.
What's the timeline of this sort of research? When do we expect to start seeing that data coming out that we can actually comprehend into anything?
Yeah, I mean, particle physics is a field that works on very long timescales. So we've been working on I've been working on June for about 10 years. Other people were doing it at least 10 years before that. Mm-hmm. We are hoping to turn on our first detector around the end of this decade. The beam will turn on a little bit after that. So at first, we're going to be measuring solar neutrinos from the atmosphere. We'll also be looking for neutrinos from supernovae, which will be really cool. If a supernova goes off, we can measure the neutrinos from that. And this is a complete diversion, but if a supernova happens, the neutrinos will reach us before the light does.
Really?
Yeah, because neutrinos almost never interact. The actual process of a supernova, the light gets sort of absorbed and re-emitted quite a lot as it makes its way out, because it's a very dense environment. Neutrinos don't care, they just leave. Yeah. So there's actually a global network of neutrino experiments called SNOOS, the Supernova Early Warning System.
It's just great acronyms in this field.
Yeah. You can sign up to get an alert if any experiment thinks they're seeing slightly more neutrinos than baseline. And the idea is, hopefully, if there is a supernova, a number of experiments will register it, and then we can point the telescopes in the right direction and see the start of the supernova, which we've never seen before. But June is going to have really good sensitivity to supernova neutrinos. Because I will say, all of this supernova early warning system, all of the planning, all of the talking about how great it would be, it's happened once before in 1987. And worldwide, I think we saw about 20 neutrinos.
Oh, really?
So, hopefully June will see many more if one happens. And we'll be able to make really interesting measurements about astrophysics and things as well.
So much of this research works in hand with the advancements of technology that are able to kind of get us to those points. And that's the case in a lot of different fields. A lot of those developments now are more software-based, whereas this seems like it's still a predominantly hardware-based advancing field. But what's the missing piece now? What would the next iteration of a big advancement look like?
After June, I think one of the most interesting things is there's an idea that neutrinos, sort of uniquely among all the particles, could be their own antiparticles. And if they are, they would do a process called neutrinoless double beta decay. So a double beta decay is when one atom does sort of two beta decays simultaneously. So you get two neutrons turn into two protons, emit two electrons, and you get two electron antineutrinos. If neutrinos are their own antiparticle, then those electron antineutrinos could annihilate against each other. And that would give, then if you measure the total energy of the two electrons that you see in your double beta decay, if there are neutrinos, you would expect to see a spectrum, just like going way back to the original beta decay thing. If there are neutrinos, there's some missing energy, and so you would see some sort of spectrum of electron energies. But if there's no neutrinos being produced, the electrons, if you sum them up, should take all of the energy from that beta decay. And we can calculate what the energy should be. So there are experiments that are looking for that, but that is somewhere where I think a lot of technology development can really help, because we need really big detectors to have a big volume of stuff that we're looking at, because it's an incredibly rare process, but also really good resolution to be able to tell that we're measuring the exact right energy. Scientifically, I think that is after neutrino oscillation is going to be the next most exciting thing. But there's a lot of other innovations. Another one is measuring the neutrino masses. The fact that neutrinos oscillate for quantum mechanical reasons that I'm probably not going to have the time to go into, but it can only happen if neutrinos have mass. And that's how we know that the neutrinos have mass and that they have different masses, but we have never been able to measure what those masses are. And so trying to directly measure the mass of the neutrinos is another big area of research. Since you mentioned technology developments, I think particle physics does drive a lot of technology developments. And part of it is, I think, because we're thinking about what we want to know about the physics and we think about what we can possibly do, but that's sort of driven by what we want to know. So, for example, I know collaborators have had meetings with engineers where they're saying, okay, we thought we'd take this big tank of liquid argon and move it. And we'd like it to move, but also be, completely solid and completely fine. If we could just move it back and forth like about 30 meters.
Yeah, easy enough.
The engineers sort of sigh and go away and come back. And the next meeting, they're like, we've thought about it some more. It'd be really good if the vessel was really thin because we don't want our neutrinos getting lost in the vessel. And that's an example, I think, of how the sort of basic science you want to do can drive innovation. A lot of cryogenic stuff has come out of Fermilab's work with liquid argon because we've learned how to manage cryogenic liquids at large scales. And that has implications in superconducting technology that's used in medical accelerators in hospitals and things like that. I mean, medical accelerators for hospitals is another thing that came out of particle physics. Proton therapy for cancer came out of accelerator development for particle physics. But as you said, a lot of the development at the moment is in software. And I think aside from the sort of pure pursuit of knowledge, one of the biggest outputs of particle physics worldwide is people who are very highly trained in big data analysis. Particle physicists have been using AI for a really long time. We called it machine learning in the 90s when people were using it at CERN. And we're one of the only places where you have data sets that are comparable to things like Google and Netflix, where you don't risk taking down huge worldwide infrastructure if you try and do tests on it. So there's a lot of output, I think, even though what we're doing is really basic science.
There's a huge amount of research across science that is respectively important and critical for each of its fields, and it can't all and it won't all be funded. So how does that affect the development of this area, and does it allow it to be explored to the extent it should, or do you find that it gets held back by that constraint?
I mean, it's so difficult because ideally we'd fund all of science and everything.
Forever.
Well, yeah, exactly. It would be amazing. We definitely are limited by the science that we can fund. I think broadly it hasn't really held the field back because, it forces us to be creative and think carefully about what we can do with limited resources. And I think that's correct. Mm-hmm. We are very strong as a field of particle physics, that we do strategize and we think carefully about what the big questions are and what order we want to work to answer them. And I think that's a real strength of the field. Something we are struggling with at the moment is there's been a real proposed reduction in particle, astro and nuclear physics funding in the UK, where the government has proposed to reduce funding by 30%, which would be a real cut. And that would be really problematic because that would potentially see us pulling out of some of these projects that we're working on worldwide. All of the experiments that we work on have been asked to submit estimates of what we would do with a 20, 40 and 60% cut. And I think, it's clear to say that something like a 60% cut to UK involvement on June would be devastating both to UK particle physics, and also we're the second biggest contributor on June. So it would also be a huge problem for that. And it's also a shame for the UK because I think it's a very, very difficult job to balance different priorities within science and outside of science. And sometimes I think the sort of really, I'm going to say basic science, for want of a better word, that is not really applications driven can seem like it's not as pressing as other fields. But I think in a long-term view, this is where a lot of the real innovations come from that aren't going to pay off within the next 5 years, but might be what we're basing our technology on in 20 or 30 years. There's also evidence that a lot of people get into science because they're really interested in these big questions, particularly particle and astrophysics. And most people who do physics degrees don't end up doing physics for a job, but do go into sort of broader innovation in industry. They're highly trained, they're highly numerate. And I think that, again, is a thing that we need to really balance carefully when we're thinking about how to weigh up these different priorities and funding. But it's a difficult time for particle physics at the moment, and we're really hoping that we can turn it around.
Well, it seems like there's so much exciting things to come out of it. So it's an area that people should get involved with as much as they can and keep posted on, because there's some huge things coming out of it by the sounds of it, which is really exciting.
Yeah. It's also an area, if I can say, that we in the UK are really having an outsized contribution worldwide. We have the Director General of CERN is British, former director of Fermilab is from the UK, and a former director of SNOWLab, which is where the SNOW experiment ran in Canada, is British. And I think a former director of Triumph, which is another lab in Canada. So like UK scientists, it turns out we're really excellent at particle physics. And yeah, there's a lot of really exciting stuff to come, and we are well placed to do it, I think.
Well, I think that's a really nice positive note to end on. Kirsty, thank you so much for joining me, and best of luck in your talk.
Thank you very much.
That's it for this episode. Thanks so much for tuning in. Kirsty's full talk from our theatre will be available very soon. Just search the Royal Institution on YouTube and keep your eyes peeled. If there's any science you'd like to hear on the RI Science podcast, do let us know in the comments below, and we'll be back next month.